Okay, good afternoon, everybody. This is the hands-on tutorial on MOA, a software system that we've built over the last 10 years. MOA is a backronym, so we claim it means Massive Online Analytics, but to be honest, there's actually a native bird in New Zealand, an extinct native bird that was pretty big, probably bigger than the biggest current birds that you have around. Of course, New Zealand was flightless as well. So I need to explain a few things first before we can actually start. There's a lot of space here, but I understand that screen over there, but also on the far end, are much better than the one in the middle. So it's a bit of a compromise, I suppose, where you want to sit. Okay. Due to some communication issues, we have actually not had this is not on any links online. So what you want to do is you want to go to this web page, moa.cms for .waikato.ac&z. And I will do that as well. So, yep. Then you should see something like this. And here in this black bar, there's an entry for today's tutorial. So if you click there and go there, then eventually something should happen. So this is a hands-on tutorial, kind of. What we're going to do is actually a mix. It's the first time we do that, so it's an experiment for us. So the idea is that we have quite a number of slides, and I'll mainly go through the slides, and at certain parts we stop with the slides and switch over to some real exercises for you guys. Now, if any of you have been to the Big Data Winter School in Bari in Italy this February, the slides here are subsets of the one that we use there. So if you have been to that one, today might be a bit boring for you, and you might consider one of the many other things that are happening right now. Just saying that they've been warned and can't complain afterwards that it was boring. Now for the hands-on exercises, what we need is that you install MOA, and MOA needs Java 8. So if you have not got Java 8 on your machine, then you probably can't do the exercise today unless you are able to install and download that in the next 20, 30 minutes or so, which may work for one or two of you, but I doubt it will work for everyone here. But yeah, hopefully you have Java 8, then you just need to download MOA software itself. And there's a much smaller package than Java 8, so that should work for everyone. Yeah, and I apologize again. We sent in a link with all the information, but somehow that got lost. And, and actually, the tutorial wasn't even scheduled on the main program last week. So we've at least managed to have you all here today, which is good. So, yeah, if you scroll down here, you see there's another link where it says download MOA from here. And if you click there and wait a little bit, then you get to a SourceForge site. So MOA, as I said, is already 10 years old, so the releases are on SourceForge, but kind of the code development is on GitHub. And eventually, probably everything will move to GitHub. But right now, there's still this kind of mix, unfortunately. So, anyone got any problems with downloading or not finding the link or any other urgent thing right now that will prevent you from actually being successful here? Yes, please. Sure, no worries. Yeah, I wanted to switch back to the slides anyway. Good point. Okay, yep. And I'll make that as big as possible. Okay, so moa.cms.waikato.ac.nz. And that is the black bar, and left bottom part of the black bar, it says KDD Hands-on Tutorial 2017. If you go there, then in the first paragraph of the next page, there's this download link for MOA. Okay, so while you are doing that, I'll actually go back to my first slide and properly introduce myself and Albert. So this is joint work. Albert Bifet, who's sitting here, He's probably going to run through all the exercises. And myself, I'm Bernhard Pfahringer. It says University of Waikato there for me still, because they've paid for my trip. But I've since moved not far away, just from Waikato to Auckland, so still in New Zealand, a different university. Probably doing the same things there, so not a big deal. Now, if you look at that with these pictures, what you get is always, you get the nicest possible picture, right? The rest of the university is a bit more like, parts of it like the usual 70s concrete, ugly old building. So this afternoon, we want to try to convince you that streamlining is something that is useful and that actually you might look into yourself as well. So, I'm going to have multiple overview slides for the various parts that we're going to cover today. I shouldn't put my hands there, because otherwise the microphone doesn't work. So I'm just going to do a little quick introduction on what is streamlining, what are data streams, how is it different from your regular machine learning. There's 5 specific challenges that you face when you do streamlining. And one of those is an idea, the non-existence of an idea assumption. And then we're going to look a little bit into a few very simple things before we move on to more interesting algorithms. So streams. If you look around, everything these days generates data. It generates data at really high rates, and that data is generated continuously, and that data may change over time. So just put like a couple of examples. You can look at plants that are managed where you may have a control room, like the one in the middle where you see like I don't know how many screens. It's not very good, is it? Because as a human there, you probably quickly lose interest in all those screens. It would be much better if you had a system where all the screens are black, and only if on one screen something happens that's interesting, that comes up, and then it gets your full attention. And then maybe you could look at other stuff around. Of course, navigation, this is kind of old already, so you probably just use your phone these days. Or you have a built-in nice navigation system if you have an expensive new car. Travel, if you use public transport. Even here, when you walk into the door and you're being scanned, conference, they know exactly which sessions you've been to, unless you sneaked out or in. Shopping, of course, I mean, all that data is collected online in various ways. But there's also interesting other types of streams, and that I picked out here is what I like to call science streams. So if you look at what's happening in science these days, people basically build sensors or measurement devices, and then they measure and collect. So a very interesting example is this Large Hadron Collider in Switzerland/France. Or for instance, if you just look at a hospital, an ICU unit, I mean, there's a patient there, you may be able to see the patient. There's a lot of machines around, and they measure everything. And of course, if you're in ICU, probably something seriously wrong with you, and so you would expect stuff to happen and change, like your heart rate might go up or down, your heart might even stop, your blood pressure might play up, and all kind of other things. Now, I'm not sure if you've all heard about the so-called square kilometer array, which is an amazing radio astronomy thing that's happening in the southern hemisphere. In South Africa and in Australia, they're going to build lots of little dishes over a large area, and basically that works as if you had a really, really humongously large single radio telescope. And it's actually mainly financed by the European Union, which are a big member of this. And these guys, they will generate unbelievable amounts of data. This is the biggest data on Earth when it's happening. This is bigger than anything else that you've seen before. This is even a lot bigger than the Large Hadron Collider. A lot bigger than all the commercial data that we collect. Because they have these thousands of dishes that all collect data in real time. So, and then you want to find interesting things, like you want to find changes or regular patterns, like for identifying quasars and other stuff. So now, I hope you agree with me that there may be some use of streamlining. The next question is, of course, you don't want to implement all the software yourself, unless you really love hacking. But otherwise, it's going to take a long time, and there must be some bugs. And it's usually much better if you can use someone else's software that has been properly debugged, and maybe also people have used it in experiments, published, and you can easily compare when you use their framework. There's actually a good number of systems out there already, and there's more that are being built currently. So, yeah, I've just put ours first, but it's not just because they're most familiar to us. There's more, and then there's a variant called Samoa, which is a distributed version. So Samoa stands for scalable. What's the A? Yeah. And then you may or may not have seen the poster yesterday. So Moa and Samoa basically use Java, live in a Java environment. StreamDM is kind of, not really a clone, but is a C++ software, if for whatever reason this is your preference. But if you look at other people's systems, there's of course Spark has now a big sub-package called Streaming. And there's an interesting architecture, the Lambda architecture, that was mentioned yesterday in a number of talks, which tries to combine online with batch processing in interesting ways. Then if you look further around, R, which is a very popular language for data science these days, has some streaming packages. And R actually has a connector to Moa. So if you're really an R person and don't want to leave your R environment, you can still use R and access Moa from inside R. The algorithms. You won't get the GUI, but the algorithms. And even if you look at other open source software packages like RapidMiner or Weka, they also have some limited online processing capabilities. There's a lot of stuff out there. Today we're just going to focus on the first one, on Moa. But it's probably equally interesting to look at some others as well. So, it's always nice to have a definition, and often we don't have good definitions. So for instance, I'm still looking for a good definition of artificial intelligence that my students would agree with. But in streamlining it's a little bit better, at least as long as you agree with me. So the claim here is that it lives in an intersection of 3 different areas. It borrows ideas from online learning, from time series, and from databases mainly. But also general machine learning as well. But I think that's a given, so I've not put that there. Now, what's so interesting or problematic about streamlining? Well, if you think about what I said, that you have these sources that generate data all the time, either at regular or irregular intervals, and also at different speeds. I mean, it might be many, or might only be a few data points per time unit. Then it's pretty obvious that you want to be able to process your data incrementally in some way. And I'll explain a few schemes for that a little bit later. So even though I say incrementally here, we can cheat a little bit at times. Now, you have all this data streaming in. So it will build up and build up and build up if you would just store it. And eventually you will run out of space. So what's needed here is that, per example, you've got to have an algorithm that is kind of efficient, in the sense that it only uses a very small amount of memory and also only a small amount of runtime. But of course that relates to the speed of the stream. If you have a slow stream, you can be more expensive with the algorithms. If you have a fast stream, you might need to be smarter. We also want to be able to predict. So for instance, with traffic, when you measure traffic flow, you want to be able to predict that there's going to be a traffic jam somewhere. Or here, when we measure how many people have come in, we want to predict that actually this room is getting fuller a little bit, but maybe there's some other rooms that are more or less empty, and so you might want to guide someone who's not really decided yet into another tutorial that has only like smaller number of participants. So you want to be able to predict at any time. And therefore, all the algorithms that we look at are usually some form of anytime algorithms. Now, number 4 is, from my point of view, the most important bit. And this is where it really is different from regular machine learning. And I'll come back to that on the next slide. And the last bit is that depending on what you measure or what you collect, you might be lucky and you might get feedback all the time. So for instance, if I measure electricity consumption, and make a prediction for how much electricity will be consumed in Halifax in the next hour. Once that hour has passed, I know what the real number was. So an hour later, I get feedback on my prediction. If I predict, pulling a number, 5 gigawatt hours, and the actual measurement is 5.2, that was pretty good. If I predict 5 and the actual measurement was only 2, I was far off. But I get this feedback automatically, but with a delay. So this is the simple scenario. Now there's this other scenario, which is a lot harder. So for instance, if I not look at electricity, but I look at Twitter, all the things people tweet about this conference, for instance. I can make predictions about the tweets, it's a positive tweet, so this person really likes the conference, or this person ran into some issues, so they're not that happy right now. If I make this prediction, I will not get an automated feedback on that ever, because Twitter is not set up to actually verify my predictions. So in this case, what you would need to do is, you would need to have some other mechanism, for instance, someone at Amazon's Mechanical Turk, to look at that and verify it for you. Of course, this is expensive, so you won't be able to do that for all the data. And this is what we mean by limited feedback. You can probably look at a percentage, and you may have smart ways of choosing the percentage, like you look at predictions where you're not that confident, or also sometimes you might just randomly choose a few, because you never know what's happening, and if you not add some little bit of randomness, you might completely miss interesting changes. So it's all kind of interesting. But as I said before, the most important bit is this IID assumption. If we look at regular machine learning, what we always do is we do some training, and then we have validation and test sets, and we assume that all these sets have the same statistical properties. So, or in other words, using statisticians' language, that the data is independently and identically distributed. So there's one underlying distribution that generates all the data. And then regular machine learning makes sense. If this is not the case, and there can be lots of reasons why this is not the case, then your prediction on a test set that has different properties can be far off, and you would not even have a good handle on how far off it can be. So here in Streamlining, we have to live with the fact that eventually something's going to change. You have sensors, the sensors get old, they need recalibration, they drift off, they break, you put in new sensors, they have different characteristics, there's different phenomena happening. Like if you look at time series, where I said we're going to steal a few ideas, there are cyclic patterns like electricity consumption. In the morning and late afternoon you have peaks, and maybe on a hot day you also have a peak around lunchtime for air conditioning. In winter you might have peaks in the night when people use electricity for heating. On weekends, patterns are completely different because people tend to sleep in, might not get up that early, so the morning peak is delayed and also washed out maybe. You might see something which is just a little higher plateau between 8 and lunchtime or something like that. So things change. Yeah. This is not just true for streams, it's also true for scenarios where people think it shouldn't be the case. So I'm not sure if you're familiar with that, but about 5 to 10 years ago, there was a big discussion in bioinformatics where people suddenly claimed cross-validation is wrong, it doesn't work. Always gives us the wrong predictions. And the problem there was that they violated the distribution assumption because they collected some data, trained a model, and then used the model to predict for new artificial data points, and then only generated or synthesized the interesting ones, so a non-random subset, and then we're expecting the model to perform well on this non-random subset, which it didn't. There's actually a couple of interesting papers that have been published about that. So it does happen. Another example, if you look at all these competitions that are popular these days, this one is already quite old, from PA-KDD, like one of the smaller cousins of this conference. I think that was in Thailand, in Bangkok. So they had data from a bank, and the training data was from 1 year. The validation data for the public leaderboard was from 2 years later, and the final evaluation data was from 3 years later. And of course, things change with financial data. First thing, this is Brazil, there's inflation. And there's inflation at a level that you can't ignore in Brazil, unfortunately. So what you see here is that people did not really account for that, most of the participants. And so they overfitted the public leaderboard. And then after the final results were revealed, turns out that the actual winner was only number 60 on the public leaderboard. So they kind of didn't really care much about the leaderboard. But also number 2 and 3 were not in the top 3 or top 5 or top 7 of the leaderboard. Not surprisingly, the winning group there was from another bank in Australia. So they knew exactly what they were doing and how they have to adapt to changes over the years. Probably a bit unfair, but that's the way it is. Another example where you see change is this one here. So New Zealand actually is really good in terms of collecting data, various things like medical data, but also government data in general. So for instance, all the accident data since 2000 is online. And this is a subset until 2014. There's about 500,000 accidents. And 200,000 of those have been labeled as that the first driver had a significant influence. And yeah, sometimes accidents even happen to the police, as you can see. Now, every time we do some data analysis, it's also good to look at data, try to visualize it. And so in this case, if we just plot the location of the accidents, what you get is a very nice outline of New Zealand. You see the islands, the 2 islands, but you also see this little additional island that for some reason also has accidents, which is kind of unimaginable, given that there's a tiny population, just a few cars. But you also see that where the people live, so this is this northern part of the North Island, there's like 3/4 of the population, and so you get a lot more accidents. And you get the main highways, and there's actually nothing, because this is basically a huge remote area. There's a national park. Also, color-coded here is blue is accident on the highway. It's in a zone where it can go up to 100 kilometers per hour, not miles. And red is in cities or towns, so usually 50K limit. So if you run some cross-validation using a tool like Waikato, you get some result, which in this case I can read out for you. It's 28% error rate, which is not that impressive, but it's a simple algorithm, so maybe okay. Now, if you actually, so this was cross-validation. Now if you actually split the data in old data, the first 7 years or so for training, and the next 7 years, so from 2008 to 14 for testing, what you see is that your accuracy drops, so your error rate goes up to 36, much worse. Now, with a system like Waikato, you'd be stuck at this point. If you look at MOA, you can actually look at like an online learning curve, for instance. So in this case, it's the same algorithm. I think it was naive Bayes, so extremely simple, but just to make a point. And you see that the prediction accuracy significantly drops at one point here. So unfortunately, it's not an interesting discovery, because what's underlying that is actually that, so that's one more interesting thing. If in a system like MOA, where we know that there will be change, and we have algorithms to cope with that, if you use a more sophisticated algorithm like bagging with a change detector, then you get the blue curve here, so a curve that somehow implicitly responds to the change and does not see the drop. Okay, so unfortunately it was an interesting discovery, because basically if you would read the 100-page manual that comes with the data, they inform you that the recording procedures had changed in 2007. And so they were a bit slack until then, and after that they were much better, but they changed the distribution. Okay, so I guess the message here is things will change, and you got to cope with it, and you might as well accept it. And it's nice to be able to cite a Greek philosopher from 2,500 years ago. It's not often that you can do that in a computer science related field. And a little caveat, why does machine learning actually work the way we've done it so far? Well, over short periods of time, if you look at snapshots, things may look static enough that you can actually do pretty well. And the very simple way to cope with change, and what's happening currently with most companies, is that they retrain their models. Like every night, every week, every month, depending on what the application is. But retraining might be very costly, and also retraining usually is not adaptive or flexible. Usually you have a fixed schedule, unless you do something smarter where you actually monitor how bad your predictions become and then use it as a trigger to relearn. For most companies, it's really an automated process overnight, over the weekend, every month, or maybe every hour, every 15 minutes. Really depends on what it is. So for instance, I'm sure that must be a similar website here, but in New Zealand now there's a couple of web pages where you can go to and look up some arbitrary property, like your own house, and get a prediction of what they think its current worth is. So if you wanted to sell, that's probably what you want to ask for, or a little bit more. And if you wanted to buy, it's probably what you not want off in the first round, but maybe a little bit less. And of course, they update the models regularly because house prices also fluctuate up and down. They collect data, and usually what they do is every month you have the sales data from the last month, and you add that. Usually have some window, you get rid of very old data, and you retrain your model. Now our claim is that we can probably do better than that. So, yeah, the current, probably inefficient way is to retrain from scratch as often as you need to. Now, coming back to what I said initially, you want to have online algorithms that are basically incrementally processing every single new data point that comes in. Well, you can cheat a little bit. So, a very common scheme, because we want to reuse what we've already done, right? Machine learning has researched interesting algorithms for 40 years or more. We don't want to throw all that out. We want to be able to reuse it as much as possible. So we can use some kind of meta schemes if you want. So a very popular setup is so-called batch incremental processing. It's actually also what the Spark architecture does. You collect a couple of data points, 500, 1,000 maybe, and then you have a little batch of data, and you do some processing with that. And then you have the next batch, and you do some more processing. And so over time, it looks as if you were working incrementally, but under the hood, it's like little batches. And if you do that, you can basically use any algorithm that we've already had. Your favorite, I don't know what it is, a random forest, gradient boosting, deep learning, whatever, in that way. And it will work to some degree. Another setup is a two-level or two-tiered setup. If you can't really think of any way of how you might turn your favorite batch algorithm into a properly incremental beast, then the usual setup is you look at bits and pieces that you can do incrementally. Usually that means you look at the data that comes in and you generate some summaries or sketches that capture what's happening in a compressed way. And then every now and then, at a second offline level, you do some more expensive processing on this current set of sketches. And you might have shifting windows over that, or you might have exponentially weighted averages or similar ideas for your sketches. So the first level would be fully incremental, and the second level would not be. But ideally, if we can, we really want to have fully instance incremental algorithms. And usually, you look at what we already have. So for instance, decision trees, there's a nice fully incremental variant of it. So you adapt an existing idea. And very rarely, you might actually generate something which is genuinely new to actually respond to a challenge that hasn't been investigated before. Another thing to keep in mind is that, I mean, it's probably true for machine learning in general, but definitely in streamlining, you never get correct results. In the sense, it's never going to be 100% correct. It's always an approximation to some degree. And so, generally, for many algorithms, you're looking for guarantees on these approximations. Like, how good are they? How close will they get to the true result? Okay. Now we're going to do a little bit more in terms of various detailed things, in terms of mainly drift and how we can detect change in drift and how we can adapt to that. And then there's another related problem here. If things change over time, we cannot do the usual evaluation that we're used to, like have a training set and a test set, or have cross-validation, at least not straightforwardly. So what we're going to show you here is variants of those that actually make sense and are efficient in a stream setting. Yeah, I probably should just very quickly skip over that. So you have things that change over time, so your models will adapt and change over time. There's lots of different axes to look at in terms of how you manage your model. There's different ways of detecting changes. There's fixed size windows, there's adaptive windows. You can weight your observations. Your adaptation can be implicit. So if you have, say, simplest setup, if you have a sliding window, then of course you can do nearest neighbor with a sliding window. And over time, if anything changes in your data, because the window has been sliding across the data, your nearest neighbor will always see the new current data, and so in a way will adapt automatically, without you having to worry about anything, to the new distribution, if there is a new distribution. The problem is, of course, how big a window do you want? If you have a small window, you adapt quickly, but then your results may not be that good because you don't have enough data to predict. If you have a big window, your static predictions might be much better, but if things change, it takes a lot longer to adapt. There's a trade-off, and unfortunately, that's the way it is. There's not much we can do about it. Except for, we might be lucky, we might be able to have an explicit change detector that helps us. With explicit change detector, for instance, what I could do is, I could shrink the window when things change, and I could grow the window when I think the distribution is static right now, and get kind of the best of both worlds. Sorry, yes?
I was wondering, like the window, is it always time-based?
Yeah, again, there's various options. In the simplest case, it's time-based. Or even simpler, in many of the experiments that we run with artificial data, it's basically the time unit is every single example. So we don't actually model different arrival times between examples. But in the real world, it can be time-based. It can be landmark-based, like you have a window for every hour, or for every day, or for every week. And so it's actually not sliding, it's one after the other. What else do you do? You can have adaptively shrinking or growing windows. There's all kind of various kind of little interesting algorithmic details that you can look at. Okay, now, nearest neighbor example is very simple, because there's not really a model that I need to train. But generally, we have a model that we need to train. Now, when change happens, the question is, what do we do? Simple thing is, of course, you just throw away the old model and start from scratch building a new one. But that's probably somewhat inefficient. Or at least you lose maybe some useful information from the past, because it may not all be bad. Maybe it's just like some aspect of the thing has changed. Like you added one new sensor, but all the other sensors are generally still collecting the same information as before. So you might want to add, for instance, a new model to an ensemble. This is why ensembles are very popular here, when you can afford to have them. Because ensembles are kind of a little bit more modular, and you can try to find bad parts and remove them and replace them with new bits, but you don't start from scratch because you have all the other ones still there. Now, when you actually do research around change detection, there's usually 3 different quantities that are of interest. You want to have the true detection rate, that you actually notice change. The false alarm rate, how often do you predict the change when it hasn't happened? And also, usually, even if you predict the change well, you probably have a little bit of a delay or latency to actually notice the change. Because the first few points that look different, you can't be sure it's actually changed, because there may be noise, there may be outliers, and with real-world data you always have that. So you usually have to wait for a little bit to become more certain or confident that you're actually seeing change and not just noise. And of course, these things are unfortunately all correlated with each other. So if you have a good high true detection rate, that usually also means you have a higher false alarm rate. It's like precision and recall. You can't easily independently increase both of them. Usually you increase one and the other one goes down, or vice versa. And same with detection delay. If you aim for very short delays, you probably get more false alarms. And if you allow for longer delays, you might get a lot less false alarms. Okay, there's a number of very simple algorithms to detect change over the simplest possible setup or almost as simple as possible. So if you look at just a single stream of one number or one measurement, like a temperature sensor in this room, that maybe has a good influence on the air conditioning. I'm not going to go into much detail here, but the slides should be online, and there's also lots of books that explain it in detail. Basically, the idea is you look at the kind of the deltas to the current mean, and if things change too much, then you declare a change. And the slightly more sophisticated version of that has been invented by João Gama and his co-authors quite a few years ago now. You will see that name quite often. João is one of the very prolific researchers in that area with his group in Portugal. So what they actually do, they look at not just the means, but also the standard deviations. And then they have this idea from process control, where it's not just everything's fine or there's a change. There's kind of an intermediate stage in the middle, where you think something has changed, but you're not 100% certain yet, and so you call it a warning state. And you might do something specific, like in the warning state, maybe we start a new model already, so that that model has a little bit of a head start if it turns out that we really have a change. So if a little bit later we declare change, we don't have to start from scratch. We already have this pre-trained model that had been started when the warning was raised. Of course, it might be the case that we go back to normal. There was no real change. Then we just probably have done a little bit of unnecessary computation, and we probably just throw that model away. Now, this is probably the most widely used change detector in streamlining. I think all the packages would implement it. That's something that Albert has researched for his PhD. The idea there is, again, a bit more sophisticated, but also really nice in terms of there's only one parameter. There's a user parameter. And even that user parameter is not really a user parameter, because it turns out that a default value, some very 0.001 like that, works really well most of the time in many problems. So in a way, you can use that almost like a black box. The idea here is that you look at, you have an adaptive window, and while you think that there's no change in the window, you grow the window. Of course, that's a bit of an issue, because if you have a very static distribution that never changes, then you would grow in unlimited ways. So they also have a smart way of compressing all the data in an exponential way, so that you can actually really, even for a completely static stream, monitor that for basically as long as you like in practice without running out of memory. And then the idea is you look at that window, and to determine if things are stable or not, you look at every possible split point and have a statistical test for, is the mean before the split point the same as the mean after the split point? If that's true, it's steady. If that's not true, then you find the newest split point where the new mean looks different from the old mean, and you cut down the window to this new smaller size and start growing again. So this can be computed efficiently, because well, it's not just a memory, it's also a side effect of the compression scheme is that you can compute it efficiently as well. Because it will be approximate, because with the older data, you don't actually have all the points, you just have summaries that are more and more approximate. But usually what you need to have is a good picture of the current near history, and like what's happened a long time ago usually doesn't matter that much anyway. Okay, this was change detection. Now is that because of this issue with evaluation. The simplest way of doing evaluation in a regular machine learning setting is you have a training set, you have a test set. Here, this is sometimes called holdout. So if you have a separate set, then you can train your model incrementally on the streaming data, and every now and then you say stop, you run your holdout set through your model, you get a prediction, you get an error. That works to some degree. Has a few issues. So for instance, you need to stop and evaluate. In the real world, that's not really possible, but you could argue you could copy the model to a different machine and have a different machine evaluate that snapshot of the model with the holdout set, where the first machine is still updating with the data that comes in while we're evaluating on the other one. But the other problem that you run into is that your holdout set needs to come from somewhere. And if you have collected it at the start, then that reflects the distribution at the start. Now, if things change over time, your holdout set is not relevant anymore. And you might still get good results on your holdout set, but it's not really a reflection of what's happening with your model and the real data. Or the other way around, it may look really, really bad on your holdout set, but actually for your real streaming data, it's much better than that. Because once the distributions have changed, and if everything's up for grabs and you don't really know what's happening. So it's not that useful, unfortunately. Now, luckily, this is really genius, simple idea. If we have a stream, we get data all the time, new data. Why don't we use the data point when it comes in for testing first? So we have a new data point coming in, we make a prediction at that point, and only after that, we actually update the model with the information from that point. So we train the model on the data point. So in a way, when we did the prediction, the model hadn't seen the new point already, so it's not biased in any way. So frequential gives you a really good idea of what's happening. And it's very simple, and it's very fast to do. Of course, it relies on that you get feedback somehow. So for instance, with the electricity example that I gave you, an hour later, you actually know how good the model was when we have the real number coming in for your prediction. And with the tweets about the conference, well, you may get some feedback for some of them, but not for all of them. Now, there's a few drawbacks, unfortunately, here as well. Initially, when you start, your model is very fresh and hasn't seen much data, so usually it's not that good. And the way you do evaluation here, you have this running totals. You might, for a long time, have a pessimistic estimate about how good or bad your system is doing, because it's been influenced by the originally bad results. Now, there's some ways around that. So fading factors are very popular. Again, like exponentially moving averages, alphas of 0.99 standard value. Or you might have a sliding window for your predictions so that you only get the frequential evaluation over the sliding window, which can be implemented quite efficiently, so it can be solved. Now, there's another problem. Well, maybe I'll show you that before I talk about the problem. I think it just if you look at the red one, this is a data set where nothing changes, so a static one. And so you would hope that your models improve over time to hit a maximum that you can achieve. Now, the holdout set, in this sense, in this setup, it makes perfect sense to have a holdout set because things don't change, gives you the red curve here. And there's these two different versions that actually here, this is the pure first test and then train, and that suffers from this initially bad performance. And here, this is one of the variants that tries to adapt, and I think that was with a fading factor. It's a bit introducing quite a bit of variance, unfortunately. It's quite wiggly. It's much closer to the holdout performance. Okay, now the big problem with frequential is you get a point estimate, but you have no idea about your distribution in terms of when you want to compare two classifiers. Your frequential will tell you it's 70.1 for one and 70.3 for the other. Now, is this difference of 0.2 significant or not? We don't know, unfortunately. So this is where frequential kind of fails. Gives you a good idea of what's happening with your model, your single model, but you can't really use it well to compare models, and also not even get an idea of how much variance is there in your stream, in your models. So it would be nice to be able to do something like cross-validation. And you can actually do that if you borrow these ideas from frequential and merge them with standard cross-validation. So now what we're going to do is, whenever first of all, we need a couple of models, so it's more expensive, but maybe you have a multi-core machine, you don't worry, or you distribute across a couple of machines. So that's not a big issue. Now, whenever you have a data point coming in, you need to make a decision on which of your models will be trained on the data point and which of your models will be using the data point only for evaluation purposes. And that opens up quite a number of possibilities. So you can model proper cross-validation this way by basically shifting your example to all your classifiers but one for training, and only one, and that's usually either in a round robin fashion or randomly determined which one it is, uses that example only for testing. It does not update afterwards. So basically in this case, all the models see, if we have tenfold cross-validation, 90% of the data, use the remaining 10% for evaluation. And you can then do exactly all the tests that you can do in cross-validation in regular batch-oriented machine learning. But we don't have to do it exactly that way. We can do it like, do it upside down. We can actually shift it only to one model for training and to all the other models for evaluation. Now the question is, why would you want to do that? That's a bit weird. We don't usually do that. That's much faster, because every model only trains on 10% of the data instead of 90%. And of course, you now have these two extremes. You can do something in the middle, which is almost bagging, or basically it's probably bagging, where depending on how you determine the subsets, you use some of the models, use the new example for them to train, and for the others use the new example for evaluation. And if you actually choose the distribution rightly, and in this case that usually means you use a Poisson distribution to determine how many, and then randomly select which ones would get the next example or not, then you can really mirror bagging. And you can do all the things that you can do with bagging, like having out-of-bag estimates and stuff like that. So it can be done. It's quite interesting. And actually it took a while to be published, even though it seems so obvious. So that was 2 years ago at KDD in Sydney. And now if you look at what are the properties of the three different methods, it's of course as you would expect. Cross-validation is most expensive to compute, split is the simplest, and bagging is in the middle. And if you look at the results, the estimates, how good your estimates are, then cross-validation is the strongest, gives you the best results and also the best significant differences, and the other's a little bit weaker. But bootstrap or bagging actually is usually quite close to cross-validation. Now, there's one more thing in terms of evaluation, where you can really fool yourself. And we have done that to ourselves as well. So shame on us. This is a typical example, a typical benchmark data set that people use in this area. That is electricity in New South Wales and I think Victoria and the interchange and I don't know, hourly or quarterly measurements. And you see learning curves here for a number of different standard algorithms. The very fast decision tree, then just predicting the maturity class or naive Bayes. So the two algorithms look reasonable, right? The baseline with maturity class, which is a good baseline, is generally worse, around 60%. And those two algorithms are probably around 80 with a bit of a problem in this area. It doesn't look too bad. I hope you agree. Well, we thought it doesn't look too bad. But then, there's this guy here, the red one. Now this one looks really good, right? It's like winning all the time, almost all the time. Not exactly all the time, but definitely top there. And this guy, it's actually, I think that's a running average of the accuracies at 85.3% accuracy. And this is from the literature, results that people have published. And as I said, some of those results we have published. And they might be here in this area, below the 85. But I think there's at least one also above the 85 from us. So what's so bad? Why is this a revelation? Well, it's a kind of different baseline. It's not the maturity class. If you just predict what happened right now. So the electricity consumption the next minute in Halifax is probably the same, more or less, as the current minute. If I have very short-term predictions for a lot of physical processes because they're very stable, I mean, there can be chaotic processes, and things are different. But for a lot of things that you measure in practice, things are very stable. And the time series people have known that for a long time, and so they usually use something like that as an additional baseline. And it's only interesting if you can beat that baseline, if you can be better than just predicting what's happened. And the example that we have here is with the rain radar images. So I'm a big fan of rain radar. I often use it. Like if I want to convince people that we should have a soccer game at lunchtime and they think it's going to rain, I show them the rain radar and tell them, yes, it's hosing down now, but in 15 minutes it's going to blow away to the west and it's going to be nice and dry here. We can really have a game. And with the rain, it's the same usually. It rains now, 5 minutes later it will still rain. So if you look outside today, predicting no rain is a pretty safe bet. And when was that? Sunday afternoon, pretty safe bet to predict rain. Now, once this is understood, and the problem actually has a name, it's called autocorrelation. So a lot of time series are autocorrelated, meaning there's a strong influence of the recent past to the next value. Then you can exploit that for prediction in various ways, but also you can exploit it for measuring. So what we tried in one of those papers is actually define a new measure that takes that into account as a new baseline. Has a few issues, unfortunately, so it's not really, we're not really fully happy with that yet. Let's put it like this. It's a start, but it could be better. And I'll show you why. Or you can try to exploit it by adding that information to your model. So not just having the input data, but also the measurements or predictions from the recent past. Maybe just one data point, or a couple of data points. So like a window of L data points in this case. Yeah, we look, I guess this is why we're not too happy with the measure. If you look at the scale here, it's now really a nice scaled measure in a defined areas, like between plus and minus 1. It can be arbitrarily negative, like minus 300. So yeah, negative is bad, basically. Tells you want to be positive to actually be better than this very simple baseline. And I think this is probably all I want to say here. Yeah, some same for another data set. Forest coverage is not really a data stream, but you can actually kind of massage that into something that looks like a data stream. If you sort the examples by elevation, then you generate autocorrelation. And so, yeah, here you see the class distribution on the randomized data set, very uniform. On the data set as you can download it from UCI, I think, which is weird because there must be something going on there. But here, if we sort by elevation, what you see is that this is probably pine trees or so. The higher up you go, the more pine trees you get. And this is all on the left is like vegetation near sea level. And there's a big thing in the middle. And there's the alpine stuff that only is at high altitudes. So autocorrelation is not necessarily only limited to time. Maybe other dimensions that also have or exhibit autocorrelation. And that's something that some people have investigated in machine learning with specific methods like conditional random fields or hidden Markov models. And you could probably argue that another thing that exploits spatial correlations are convolutional neural networks that exploit the spatial correlation in an image, your local neighborhood. But generally speaking, I think this is an area where there could be a lot more work. Okay, now we should have a break for some actual exercise to get you more engaged. And Alva's going to take over for the first 4 exercises.
Okay, so everybody has it? So, yeah, let me continue trying to explain what we're going to do. We're going to do the first 4 exercises. So first, yeah, let's we have the download the software, so now we can run the graphical interface. So MOA can be run from the graphical interface, from the command line, or from the Java API. So we'll start from the graphical interface. So yeah, the idea is that what we see here is that we have 3 different areas. The top with this configure button where we can configure what is the task that we are going to perform, where we're going to set the parameters. So that means what is the valuation that we are going to use, what is the classifier that we are going to use, what is the stream that we are going to use, how many instances we're going to use. So that's how we specify the task. So basically in MOA, what we do is that we run tasks, and the tasks in this case are evaluations. Okay, so here we see we are going to set the task, and then we'll see here we are going to get the results, and here we are going to see the measure. So let's run an experiment. First one, so let's do evaluate interleave test, then untrain. I'm going to choose learner. I'm going to choose a naive Bayes. Okay, so we have now the naive Bayes. Then from stream, we are going to use this random tree generator. This is an artificial generator that is going to perform is going to create a stream that belongs to a tree that we have generated before. So then it's going to be very good for testing classifiers. Okay, and then we have the evaluator, that in this case is the basic. That means that we are going to take the accuracy from the beginning of the stream. So another option we'll see later is to use frequential evaluation, and then we use a sliding window of the last 1,000 instances. But in this case, with this evaluate interleave test and untrain, we're going to have the accuracy from the beginning of the stream. We need to define how many instances we want to run. In that case, let's try 1 million instances. And we are going to sample using 10,000 instances. Okay, so yeah, this is now we have the command here, evaluate interleave test then untrain with 1 million instances and sampling every 10,000 instances, and then we do run. We click a run button, and then this is where we see we are going to have in the middle we'll see all the results of the evaluation. So we can see that this is like a CSV file. So we have learning. Yeah, the instances that we have used, learning evaluation instances, evaluation time, model cost, classified instances, classified correct. Okay, so this is all the data that is in CSV file. But the nice thing is that we can look at here in the bottom the plot of the graphs. No? So we see, for example, if we look at accuracy or kappa statistic or kappa temporal statistic, we see how this performs. In that case, this is a naive Bayes, so we see that it's very stable with the performance. The accuracy is around 73.63. Okay, so now if we change that and we change this to Hovding tree, this is the streaming decision tree, okay, very fast decision trees. We put this Hovding tree, we see that then the accuracy, the result is going to improve. Okay, so now if we compare both, so we see that blue is naive Bayes, and the red one is the Hovding tree, decision tree that is getting much better. Okay, so this is the graphical interface. So there are these three areas. In the first one, we see the different tasks that we are running. So we can also pause, resume, cancel, delete them. Here is where we have all these results as numeric values that then we can use this to export to other tools as Excel or Giniplot or whatever we want to plot the graphs. And finally, here we have these plots where we see how these measures evolve over time. Okay, so let's go back to a hands-on tutorial. So we see that this is the graphical interface. So we see that there are these three areas, and then basically we are going to be using this to run the experiments. So remember that we are dealing with streams. So as Bernhard explained, we have these requirements. So we need to process one example at one example. So we don't store all the data set and then we process we build our model. So we do that one instance by one instance, one example by one instance, by one example. We use a limited amount of memory, so we cannot store all the data. So we are not storing the data. We are only looking at the data and then updating the model. We need to be fast, so we work in a limited amount of time, and we should be able to predict at any time. Okay, so this is what the requirements of this. That as you can see, this is very different from the byte setting. So just to see the difference from the batch setting, let me show you an example using Weka. So imagine that we want to perform a standard evaluation on Weka. So what we do is that we open a file, we get the data set. Imagine that we get this electricity data set that Bernhard discussed before. So we have these are the instances that we have. These are the attributes. Then the final one that they want to predict if the price is going to go up or going to go down. So basically here we have all the data set in memory. We go to classify. We decide which classifier we are going to use. In that case, imagine to make it fast, we use this 0R, that's the majority class. And then we can use, there are several options for evaluation. We can use a different data set for testing and training. We can do a split, so we can divide the data set, I don't know, 66% of the instances to train and the rest for training, or we can do cross-validation. That means that basically we divide the data set in 10 parts, and then we use 9 for training and 1 for testing, and we do this 10 times. Okay, so let's do one example. So in that case, we do this using this majority class, so it's really, really fast. And you see, we run this, and then at the end, we get only one value that is going to be the final percentage. In that case, the accuracy. No, we have that using this, the accuracy is going to be 57. If we choose a decision tree, then imagine that we choose the J48, that's like C4.5, and we divide it not to do cross-validation, we do percentage split. We run this, and then at the end, what we are going to get is that we're going to get, again, the accuracy, but we are going to get one model, okay? That this is going to be the tree. So that's how this is done in the standard batch setting. No? But again, if we go to our streaming setting, here we are not building only one model. So what we are doing is that we are updating our model one example by one example. So this is why we are not going to have only one value of accuracy. We are going to have a sequence of values of accuracy evolving over time. As Bernhard said before, we have these different evaluations in streaming. So we have holdout, that is like the same as in batch. So we have data for testing and data for training that is going to be different. It's going to be independent. And then we have this interleave, test, and train, our sequential. So the idea here is that every time a new example arrives, first we use it to test and then to train. Okay, so that's the two main approaches that we have for evaluation. In the case of this last sequential, where we use the instances first to test and then to train, we have basically two ways to do that. One is we can consider accuracy from the beginning of the stream, or we can consider the accuracy from the last sliding window. So I mean, we take the average of the last 1,000 instances, for example. Okay, so this is the main two ways that we can do this. We can also, instead of having a sliding window, we can have fanning factors, and this is going to be similar to this. Okay, so now we get to the fun part of the exercises. So let's try to do these two exercises. So I think it's a very good way to start familiarizing with MOA. So the first exercise is to compare the accuracy of the holding tree with the knife-based classifier for a random tree generator stream of 1 million instances using interleave, test, and train evaluation, and using for all exercises a sample frequency of 10,000 instances. Okay? So, yeah, I think I like that. I'll give you some time if you can do it, and then we'll do it. I'll do it together for you. So, again, does everybody has graphical interface running? Yeah. Okay. Okay, so let me do the first one with knife base. So remember, so we have the graphical interface, so we need to define what is the task. So we go to configure, we need to choose the task. In that case, it's going to be evaluate, interleave, test, then and train. Yeah, let me try. Yeah, maybe better now. Yeah, I think that's the best. Yeah, so yeah, I think that's much better. Okay, so yeah, let me explain it again. So first we need to configure, we need to select which task we're going to run. So in that case, yeah, instead of all the others, we're going to select evaluate, interleave, test, then and train. We're going to select the learner. In that case, it's a knife base, so that's the one by default, so we don't need to change anything. The stream is also this random tree generator, so we don't need to change anything. Instant random seed is one, so we don't need, it's fine, we don't need to change anything. The evaluator is going to be this basic classification performance evaluator, means that takes the accuracy from the beginning of the stream, so it's by default, so we don't need to change anything. Instance limit, so how many instances? By default is 100 million, but in that case, we will use only 1 million. Time limit, yeah, we are not going to use this. And then sample frequency should be 10,000 instances. Okay, so we take 10,000 instances, and we have it. We click OK, and then we run it. So we run the experiments, and now we see here how it goes. Okay, so the accuracy is going to be 73.63%. Okay, so this is knife base. So now what we need to do is to do that also with the holding tree, and then compare and see which one is the best. So the holding tree is the decision tree that we are going to explain after these exercises. So this is a very fast decision tree. Okay, so we'll see if it's more accurate to use this knife-based classifier or to use this holding tree classifier. So basically what we need to do is to change the classifier, run the same experiment, but changing knife base by the holding tree. Okay, so yeah, let's do it. It's very simple. So we go to configure. Here in learner, we're going to change it. And instead of knife base, we're going to select trees. We're going to classifier trees, holding tree. You see that the classifiers are sorted by families. So we have different families. We have active, base, drift, functions, lazy, meta, multi-label, rules, and trees. So in that case, we go to more classifiers trees holding tree. We select it, okay, and we don't do any other change, and then we run it. As you see, in that case, it's very fast. We are running 1 million instances, and it's in around 6 seconds. Okay, and here you see what is the learning curve. You see that how its performance accuracy is improving over time once the tree is growing and is getting much more instances. So if we click over the previous one, the knife base, we can see both, and we can see the difference between the accuracy of the knife base, that is 73%, and the decision tree, that is this one in blue, that is 94%. Okay, so in that case, we see that the holding tree, decision tree is is much better classifier for this data stream than the naive Bayes. Okay, so that was the first exercise. So yeah, now we can go to the second one. So second one is compare and discuss accuracy for the same stream of the previous exercise using 3 different evaluations. So now we are going to compare with the different evaluations. We are going to compare with periodic held out, with interleaved test and untrained. This is the one that we have been using. And then with frequential, with a sliding window of 1,000 instances. Okay, so we are going, again, run the 3 experiments and then see the differences that we get in the evaluation. So I'll let you some minutes to try to do it, and then we'll do together. Okay, let me do the first one, periodic held out with 1,000 instances for testing. So let's go. Okay, in that case, we need to configure the task. We'll go select this evaluate periodic held out test. Again, learner, I think we should compare with the housing tree. Okay, so that's fine. The stream is the same. The evaluator is the same. Test size, in that case, we say that we're going to test 1,000 instances. That's the difference. Train size, we're going to train 1 million instances. Okay, 1 million instances. And the sample frequency is going to be 10,000, as the other case. Okay, so we have changed the test size and the train size. Okay, we have it, and then we run it. Okay, so that's and then we see what's the performance, and we can compare this with the we can compare with the interleaved test then untrained and with the hold out. Okay, let me. Okay, and then finally, we can try this frequential with a sliding window of 1,000 instances. So in that case, the only thing that we need to do is configure and go to frequential. Again, choose a housing tree. And yeah, we have the same stream evaluator. We put the limit to 1 million instances. We sample to 10,000 instances. Okay, and that's all. Then we run, and then we see. So yeah, this is what Bernhard explained before. So what we're going to see is that if we compare the three, this is the interleaf test, then untrain. This is the red one. This is the one that is more smooth. But if we compare the periodic held out and this frequential, they are basically very, very similar. So this is why using this win frequential using a sliding window, we are having the same evaluations results compared similar to the ones of the periodic held out. Okay, and then yeah, now let's go to the two other exercises. So in that case, we are using this random tree data stream that was static. So now we'll see what happens when we use streams that are evolving over time. Okay, so in that case we have these two. This is our rotating hyperplane. So it's an hyperplane that has a speed of rotation, and then it's going to be changing. So if we have a static classifier, we are going to be doing quite well at the beginning, but when the hyperplane is going to be moving, our classifier needs to be updated. If not, it's not going to work. And then this random value-based function generator, the idea is that we are going to have several, we can decide how many centers we are going to have, and then we are going to create data examples, and then we are going to, each one of these centers, these like centroids, are going to have one class. And then once we create a new artificial point, we are going to, it's going to have the class of the nearest centroid that we have. And then what we are going to do is that to make these constants moving, these centroids are going to be moving over time. And then yeah, we also will need to have adaptive classifiers. Okay, so yeah, this exercise is basically is only we need only to change the stream. Okay, instead of using this random tree generator, we are going to be using this random radius-based function generator drift, and we'll see how these static classifiers perform with this data. Okay, so I'll let you. Okay, so yeah, basically the only thing that we need to change is, let's say we have evaluate interleaf test and untrain, we have housing tree, we're going to change the stream. Instead of random tree generator, we are going to select this random radius-based function generator drift. We're going to select a drift of 0.01. Okay, and then yeah, let's maybe start with the knife base and see how it works. So yeah, we see that the performance is really not very good because it goes to 53% of accuracy. And then if we look at the housing tree, yeah, we are improving a little bit over knife base, but still we see that it's not able to adapt to the changes. No, it's going to down to 57. So that was this exercise 3. So if we go to exercise 4, here the idea is that we would like to compare now with this three classifiers: Hosting tree with majority class at the leaves, Hosting adaptive tree, and OSA bad bagging with 10 Hosting trees. So yeah, let's start with the first one. Basically, the Hosting tree, this decision tree is a tree that uses knife base at the leaves. So we need to say that it's going to use only majority class. We need to change this parameter that is in leaf prediction. Okay, it's a majority class. And then we run the experiment with this. And still we see that the performance is really not good. It's 51%. If we look at kappa statistic, it's 3%. It's near 0, so it's very bad performing. So the next one was the Hosting adaptive tree. This is a decision tree that is adaptive, that uses Adwin, so it's able to change and evolve the tree and adapt it to the changes. So here we see that, yeah, if we compare the standard Hosting tree with adaptive tree, we see that the adaptive tree is able to adapt to the changes. And finally, if we run this with this ensemble of 10 classifiers, this OSA back Adwin, we need to go to meta, OSA back Adwin. By default, is trend is 10 Hosting trees, so we don't need to change anything. So we run the experiment with this. And then, of course, now we are using 10 decision trees, so it's going to take much more time. But yeah, using an ensemble has the advantage that the accuracy is going to be much better. Yeah, so we see now we have 36% after 24 seconds. So remember that we can look at the previous one. So we have here, we have all the different tasks, evaluations that we have been performing. So we can click them, and then this is going to appear as the first value, the red one. So we can always compare to the current one and the previous one. So here we are comparing, yeah, the Hosting adaptive tree with this one that is the Hosting tree. Okay, so we see that the Hosting adaptive tree was better. So now the bagging is finishing. So yeah, we see that this OSA back Adwin using 10 classifiers is, yeah, the accuracy is 68. That is a little bit better than this using only one Hosting adaptive tree, that the performance is around 66%. Okay, so yeah, now that was we have been doing the first 4 exercises. So now, yeah, we'll continue with Bernhard looking at the specific algorithms for data streamlining that most of them are implemented in MOA.
Yeah, so now I'm going to try to explain very quickly in a kind of a high-level way the various algorithms that you've just seen in action, so that you get a better idea of what they actually do, how they work, and how they achieve the various results we saw. So we're going to talk about decision trees in a stream setting, and we're going to talk about ensembles. And with ensembles, we look at the usual bagging, boosting, and something which is kind of a simplified version of stacking as well. So, decision trees. If you think about how they work, in batch learning, you have an amount of data, and you find one good split, and then you do that recursively until you hit some stopping criterion. Maybe you have a pure data set, there's no need to split any further. Maybe there's only a few points and you don't want to go any further because it will be very unreliable. Or maybe you have explicitly set a maximum depth or something like that. And usually in batch learning, you also prune. And prune is very important, pruning. Here, it's kind of different, but similar in a way. So we don't have the full data set. We have instances coming in one after the other. So what we're going to do is we're going to try to approximate the same process. So at first when we start at the root, but then at every internal node later on. An example comes in, we update some kind of statistics at that node so that at some stage we have enough information to be able to choose a good split. Hopefully, exact same split as the batch data would have given us, but generally that's not the case. It will be similar, but not the same one. So basically you have data structure, and if we only look at nominal attributes, then we basically just need to update counts. We need to know for every attribute, for every possible value, and for every possible class value. So you have a triple as index, you need to count. How many examples have we seen? Or if we have weighted examples, there's not a count, but a sum of the weights. But it's just a simple generalization of counting. So the interesting bit is here, basically, over there in the middle. So in theory, after every single example, but in practice, because that's too expensive, we do it after k examples, like after every 50 or after every 100. We use the statistics to compute for every single attribute what its info gain would be. And then we look at the best one and the second best one and look at the difference between the two. So in a way, what we want is we want to be sure that the one that we choose as the best one is really significantly better than all the other options. And, well, that means we need some statistical test. And the usual test here is the so-called Höfting bound, which is an interesting measure because the range of the value is part of the formula. And then there's this typical log 1 over delta factor, known as confidence. And more importantly, it's over 2 times the number of examples that you've seen so far for this node. So because I take the square root of that, that means that it's kind of slow in committing because you need like 100 times as many examples to be 10 times more confident because of the way the square root works here. But once you are confident, then you split on that attribute, make a branch for every possible value, and set up the data structures. And you can do that recursively. So, sounds very simple, has a few problems. And this is where the engineering bit comes in. So, for instance, if you have the unlikely case that you have 2 identical attributes, but maybe the more likely case that you have attributes that are very similar, highly correlated, then the difference in information gain between those two, they're identical will always be 0, so it will never be big enough. And if they're very similar, it will take a long time to become significant. So usually, unfortunately, there's not a user parameter that basically says, at some stage, just split on this attribute, even though we're not 100% certain that this is the best one. But we need to see some progress. We want to grow the tree a bit further. And as I already mentioned before, computing that is kind of expensive, so you don't do that for every single example, but you wait for 50 or 100 or even more. Another issue is with this simple method, because eventually we split the node and then we go on, this has the potential to grow a really big tree. A tree that, if we are patient enough and if we put in enough data, like instead of 1 million, 1 billion, or more than that, we will run out of memory. Because the tree is going to grow without bounds. We can't have that in the stream setting. We need to do something about it. And usually, again, that means another user parameter where generally you limit the size of the tree by having a maximum number of nodes. But it is a little bit more flexible than having a maximum depth. Because you could have a shallow part here, the very deep part here, if the sum is still within the total. So that usually works better than just a simple depth limit. And then there's more sophisticated ways of saving some memory, because these statistics take quite a bit of memory. So a node that looks really like a very confident leaf, we may stop collecting statistics there, kind of freeze it in a way, and then be able to reuse that space in some other part of the tree where there's more change happening, where it's more interesting. Now, because we wait quite a bit, namely we don't evaluate after every example, but after every 50 or 100. And we wait until the difference is significant, or we are not patient enough anymore and we have this parameter that says split anyway. It means the trees tend to grow pretty slowly initially. So sometimes if you want to have very good performance very quickly, there's this simple idea to actually just collect the first 10,000, 100,000 examples and generate a tree in a batch setting, and then basically turn the tree into a Höfting tree and update it from then on. So it's like a little head start at the beginning if you want. Now so far I was assuming nominal attributes. They're easy, they're just counts. They don't need to update, or sums of weights. Numeric attributes are a bit more tricky, because remember how the decision tree works. You sort the data by that attribute, and then you find the best possible split point. So you sort, and then you scan. Sorting means you need to have all the data. We don't. So we need to do something more approximate. There's two extreme options. One that has been described in the literature early on was actually, instead of having the counts for the nominals, keeping all the values in some data structure like a B tree to make some of the processing a little bit faster afterwards. But again, this needs quite a lot of memory. So this is why this alternative was developed, where you do the extreme opposite, where we're back to weight sums basically, where we make this very crude assumption that the data for this attribute has a distribution, and because we don't know any better, we assume it's a normal distribution, and then we just estimate the mean and the standard deviation. So we need three different sums: the sum of the weights, and the sum of the squares, and the total number. Now, of course, this is kind of two very extreme opposites, and there's a spectrum in the middle. And as far as I know, I haven't seen any publications where people would have explored these options in the middle a bit further. So you could look at something like discretization, so that you actually turn the numeric range into a number of ordered or maybe not ordered possible bins or intervals. Or some other form of incremental discretization maybe. Alternatively, if we build up these B trees for every single value of every single attribute, why don't we just keep the examples in the first place? So instead of having counts, just keep all the examples. And then at least we could do the sorting again. And we could also exploit that for other purposes, as I'll show you in a minute. So this is with a normal distribution. If you look at this example, we assume a two-class example, and we have the statistics per class at that node. And so in this case, we get reasonably nice separation between the two classes, and presumably you would compute a split point somewhere in the middle. And this is what this bar here indicates. So this is probably the best possible split if I only look at these 10 options. We only look at these 10 options because in the two-class case, we can exactly compute that point. But in the multi-class case, we can't. The multi-class case is much more messy. And so the heuristic solution for that is you look at the full range and then just look at equally spaced number of possible split points and compute an info gain for all of those and choose the best one, which in this case happens to be almost exactly at where the properly computed one would have been anyway. Now, with this expensive counting at nodes, it's a lot of space. It was obvious that people thought about that, and well, maybe we can use that for something else. Because if we look at that, these tables and the distribution assumptions or whatever, they look exactly like the data we need for naive Bayes, right? And so, in a way, we have a free naive Bayes model at every leaf, because we need to update those numbers anyway. So when it comes to prediction time, the idea is, well, let's use this information and do not just predict the most likely class at the node, but actually use this local naive Bayes model to give us maybe a better prediction. Now, unfortunately, it's not necessarily better, especially initially when you have not seen many points. It's pretty rough, and the majority class might be a better estimate than the prediction that it derived from 10 or 20 examples. So in more, we have an adaptive way at the expense of one more count, where we basically just keep track of whether a maturity class is better than the knife-based model or not. And every time we need to make a prediction, we just look at that count and then decide go with the knife-based model or go with the maturity class. If you select the adaptive version, as Albert just showed you before, you can also manually specify that you always want to have the maturity class, or you always want to have the knife-based model. Now, what I mentioned on the previous slide in terms of dealing with numeric attributes, if we were to collect all the examples instead of the statistics, then we could do something similar, but it wouldn't be knife-based. It would be a local k and nearest neighbor model. Because we go to that leaf, and there's 20 examples there, and then we can compute which is the closest to my query point, or which are the closest 3, and average them. So I could do exactly the same thing that I could do with the statistics. It's a knife-based model. Okay, so far the trees did not in any way bother about possible change in the stream. Now the interesting thing is that if you let the tree grow as much as you like, then in a way the tree will over time adapt to the change. Because what's happening then is, if you assume that you have learned a very good tree for your current concept and there is a very abrupt change to a very different concept, then effectively, if you don't do anything smart, just go on learning, what will happen is that tree will grow sub-trees that represent the new concept for every leaf of the old tree. So it will be very inefficient because you'll have, say the old tree had 10 leaves, you have then 10 copies of probably more or less the same tree for the new concept, all being rooted at the original leaves. So what that means is you need a lot of data to actually do that, because if you have 10 trees that are all copies of each other, you need 10 times as many data points to get there. And so it's inefficient, but it would, in theory at least, work over time. Now it can be smarter, and there's a lot of ways of doing that. So one idea is that you monitor the performance of every node and notice that this node was very good, it had like 90% accuracy rate, but suddenly it has dropped down to 60 or 50. Something's up, you might want to do something. And then one thing to try is prune bad subtrees, or if a node looks really dodgy, start growing an alternative tree there, and then at some stage switch, flip over, remove the old one, and put the new one in place again with some kind of statistical guarantee, usually a Höfting bound. So there's a number of different implementations of these ideas. There's the concept aware or concept drifting very fast decision tree. There's a variant of that. So this is from the guys who did the original very fast decision tree, Halt et al. Then João Gama has done a variant. Albert has also looked at using the Edwin change detector inside a Höfting tree, and they called it the head tree, where you basically have an instance of Edwin in every single node that basically monitors prediction performance. And then we also looked at Höfting option trees, but I think I'll skip that in the interest of time. It's just a little variant of trees that have multiple options. They're kind of in between trees and ensembles. As I said, I'm going to skip that. Brings me to ensembles, and we already saw an example when Albert did the bagging. So generally, common wisdom in machine learning globally is ensembles just work. They work better than single classifiers for a number of reasons. And there's different popular methods, and well, yeah, I guess bagging, boosting, and stacking are the favorites, but there's a lot more, of course. And there's a lot of arguments of why it works. So for instance, just a probabilistic argument, if you have 3 classifiers that have error rates of 40% and that commit errors independently from each other, it's important, then just by statistics, you get a reduction of the error rate to 35%, 35.2 to be precise. But it's only true if the errors are independent. So you want to have classifiers in your ensemble that are not extremely well correlated. But again, there's a bit of an issue if you think about it, because you want to have very good classifiers. So the best possible classifier is the optimal classifier, but then another optimal classifier will be extremely correlated with that one because they're both optimal. So you have a trade-off of reasonably good and reasonably not correlated. And finding that sweet spot is not that easy. And there's a lot of other potential explanations of why ensembles work that have to do with the representation, with biases for search, and so on and so forth. If you look at bagging, batch setting, it's very simple, right? You do these bootstrap samples, and we know that bootstrap sample has the same size, but it has duplicates. So if you look at the original data, roughly there's 63.2% unique examples of the original data in every bootstrap sample. In an online setting, we don't have the data to sample from, but luckily we can kind of emulate that with a Poisson distribution, because, interestingly enough, a Poisson distribution with a mean of 1 gives you almost exactly the same percentages. So I've just plotted a few here. But this one is the one with mean or lambda of 1. And what you see is about 37% have 0, or a count of 0 not being used. This is exactly 1 minus the 63.2, roughly. And then you get the same number that are only there once, but you get 18% roughly where you have 2 copies in your bootstrap sample, and you have 6% where you have 3 copies, and then it becomes more and more unlikely. But once you have the Poisson distribution, no one says that you have to stick to a mean of 1. You can try different values. And so I've plotted 6 and 10 here. They become, or they then look a lot more like a normal distribution, even though they're not really are. But we'll see that that might be useful in a minute. Okay, so this is the online version of bagging. And there was described a long time ago by Osa and Russell. So you initialize as many models as you want, M, say M is 10 in the example that we saw. And then whenever we have a new training example, for all of those models, we compute a weight for this example with regard to the model using the Poisson 1 distribution in this standard setup. And so that might be 0, then we ignore the example for that model. That might be 1 or 2 or whatever. And then we update that model with this example where we set its weight to this outcome of the Poisson distribution rule. And then prediction is like in batch setting, you average over all the models that you have. Very simple, very straightforward. It works to some degree. What we found is that in a lot of experiments that we ran, we can do a little bit better by something which we call leverage bagging, and published a few years ago, where we actually make this mean of the Poisson distribution a user parameter, and often values around 5 or 6 work pretty well. But also, maybe more importantly, we equip every single ensemble member with a change detector, so that over time we can see that maybe one of the classifiers is drifting away and doing really badly, and then, well, let's cull that and start a new one. But we have an ensemble, so it's not going to be a dramatic change in prediction accuracy, because we're not starting from scratch. We just replace one ensemble member. Okay, so I already mentioned that with ensembles in general, you want to have this trade-off. You want to have good models, but also models that are not much correlated with each other. Now, how do we judge that? Well, there's some ways of doing that. One way to visualize is to look at these so-called kappa error diagrams, where for every pair of your ensemble members, you compute how much they agree or not with the kappa statistics, and also compute their mean error. And so if we do this for one specific data set, so this is, suppose, something like 20, 25, must be more, 30 classifiers. If we compare the OSA bagging, or online bagging as it's called here, with the leverage bagging, we see a distinct difference. So in terms of the error rates, they are kind of on par in the same area. But in terms of the kappa statistics, the regular online OSA bagged ones are much more similar. The kappa statistic is much closer to 1. 1 means perfectly the same. 0 means completely randomly different. And so This is still reasonably high. It's not very uncorrelated, but at least it's sufficiently better than the standard online version. So this is a possible explanation why, in our experiment, we actually see improvements. Okay, boosting. Yeah. Okay, this is correct now. Yeah, a long time I had an error on this slide. So boosting tries to reduce the bias, whereas bagging basically just reduces the variance because we average over a number of independently generated classifiers. Bagging has this advantage that it's absolutely parallel. You can generate 10,000 trees in parallel if you have the infrastructure for that. And you're done at the same time as you would be done for a single tree. With boosting, unfortunately, it's inherently sequential. You train the first tree, and then you train the second tree because it tries to make up for the first one, and so on and so forth. So the idea is that you reweight examples to make up for the errors. The ones that are correctly predicted get a lower weight, the incorrectly ones get a higher weight. Now, in an online setting, it's a little bit more tricky because, again, we can't compute all the predictions of our set and then compute an error rate and use that for reweighting. So we need to estimate all that. And this is what this algorithm basically does here with these sums, where you update weights for the models and weights for the examples on a per example basis. And to add a bit more variance, they also use a Poisson distribution inside here, in addition to the weights, which is kind of surprising. And I can't remember if they actually compared the non-Poisson modified version to this, what they actually advocate as the algorithm that you should be using. But other than that, it's just like standard boosting. Now, an interesting insight here is that even though boosting is sequential, here in this online setting, we could use pipelining. We could have the first example coming in to the first tree and being passed to the second tree, and the second example can already be processed by the first tree. And now, first example goes to the third tree, second goes to the second tree, and the third example goes to the first tree. So, say you have 100 trees. After the first 100 examples, you keep all the trees busy in your pipeline. So again, that might be quite an interesting way of speeding up boosting, even for non-streaming data. But as far as I know, that hasn't been published yet by anyone. Now, if you look at batch machine learning, what works really well there these days, to be honest, are more complex ensembles. If you look at programming competitions, if it's not deep learning that wins, then usually it's some complex ensemble, like back boosting or XG boost, which is a very sophisticated gradient boosting algorithm, or some kind of stacking. So, of course, the obvious question then is, has anyone done this for streaming? And the answer is, unfortunately, no, not yet at least. So again, there's some opportunities there. So maybe get an XG boost version for streams, or, well, actually, the back boosting, we can probably do that right now, but I don't think I've seen anyone evaluating it and exploring it. Okay, a lot more, of course. So random forests are basically a very special case of bagging that works really, really well. And because we have a random Höfting tree, because we can easily randomize the Höfting tree, which is actually quite cool because it needs less space, if you think about it. Because what we do is, we don't set up the full counting infrastructure for every attribute. At every node, we make a random pre-selection. We only monitor those 3 attributes of this node and these other 5 of that node. And so the random Höfting tree actually can grow bigger in terms of the total memory consumption, which is good because usually those random trees need to be bigger to get good performance. And again, we can do that inside some of our bagging setups. So for instance, if we use a monitored version, then we could even notice that some of those trees kind of drift away and are not very good anymore. We want to replace them with something better. And then we've looked into a couple of other things, like stacking small Höfting trees where at the second level we use a perceptron, so kind of learn the weights for voting instead of just having a simple average usually gives you a small improvement, so it's probably worth it. Or ensembles where we adapt the size of the trees in interesting ways to make sure that they're not correlated with each other. So small trees and large trees, basically. Or this is an algorithm that will be in the next release of Moa, isn't there yet? Very simple. Basically, it's inspired by stacking, but a trivial version of stacking. You run a couple of very different algorithms in parallel, and because we can monitor performance in an online way quite easily with our streams, we basically just keep track of which of the, say, 5 or 50 different models that we update is the currently best performing one. So every time we need to make a prediction, we just look at the current best performing one. Now, this sounds very simple, and one would think or hope that being a little bit smarter, like averaging the top K or something like that, should give you an improvement. But it turns out that so far we have not been lucky in that regard. So this very simple thing that just chooses the best one every time. It's kind of related to, it's not exactly the same, but in a way related to just using the previous prediction, this baseline, seems to work really well. And it's just an example of the electricity data where, is that actually, yeah, so sorry, I don't have the nice graph here. But basically what you see is, so this blast version is almost as good as leverage bagging, but at least in this setup it is faster, because leverage bagging has quite a number of trees, and for this setup here, blast only uses 5 different simple classifiers. And in terms of runtime, as you see here, then it is definitely better than leverage bagging is the worst, but it's also in terms of accuracy, at least nominally the best, but according to this test, there's no significant difference between the top 3 anyway. So I guess the message here is if you are in a somewhat resource-constrained environment, that might be a nice little algorithm to look at. Okay, it's exercise time now, but on the other hand, we have a coffee break in 3 minutes. So I would suggest that we just start the coffee break now, and we do the exercises when we come back at 4 p.m. I hope to see you all back at 4 p.m. Thanks. Enjoy your coffee.